9 days left before Christmas, I was at a dramatic crossroads, like in that Yu-Gi-Oh card. I could add sprites or I could add interactivity. It was time to refresh myself on how DMA works. Direct memory access, or DMA, means memory access without the CPU's attention. OAM DMA is how the CPU copies a sprite display list to the PPU. It reads each of 256 bytes from the CPU's work RAM one after another and writes it to a PPU register. This is much faster than having the CPU do the copying because it doesn't need to read load and store instructions. It bypasses the so-called von Neumann bottleneck of squeezing instructions and data into the same bus. The NES also uses DMA for sampled sound. My first DMA routine would only cover OAM DMA because every game uses that and not every game uses sampled sound. I had to put another layer between the CPU and memory, one that could briefly pause the CPU to process DMA. The DMA unit does different things on odd and even cycles. On some cycles it can read things from memory, and on other cycles it can write things to memory. The NES community refers to them as get and put cycles. I had an incorrect idea of how DMA starts up, which just happened to work out this time. I did one little refactor to handle the DMA unit's startup time. I called it tick APU because sound shares DMA's get and put state. Spoiler! Later on, I'd end up hanging all of sound off this function. I'd eventually need to add reading buttons from the controllers. I already had two headless front ends, one for the NES test log and one for generally emulating an NES. I added a knob to the build script so I could run either. Good news, the new layer didn't break NES test. I added some logging for get and put cycles. I more consistently made tick APU responsible for CPU cycle counting. Something started to click in my head. It wasn't waiting for put. It never waits for put. After the one warm-up cycle, it was waiting for get. All I got done was a first draft of OAM DMA. I don't even know if the data made it in. At least I can make writes go in when the PPU isn't rendering. Day 2 of Sprites. I started by adding a way to dump OAM. If it's all zeros, then the writes didn't make it in. I added logging to tell why. Turned out DMA was writing to the wrong address. I bet this brain fart was primed by my experience programming games. Almost no games write sprite lists to the PPU a byte at a time. They always write using DMA. It was so universal that I forgot what address on the PPU to write to. I accidentally set the DMA register as the target for DMA. That looks like an OAM table. Two of my own games won't show their title screen yet. They both need Sprite 0 hit. Sprite 0, the first moving object in OAM, is special. When it's drawn overlapping a solid part of the background, this sets a bit of a PPU register. That lets the CPU know how much of the frame the PPU has drawn so that it can switch the scroll position or graphics bank. One of the games also needs the player to press a button first. I really should have put the get-put parity change after the memory reader write in the order of operations. That would have been easier with defer, but we don't have defer yet. Remember Open Bus, how the wires connecting the CPU to the outside world hold a charge? It turns out one sound-related address doesn't affect Open Bus. I forgot the exact details, so I left a note to finish it. On every line of the picture, the PPU reads sprite positions in OAM to find what moving object should be drawn on the next scan line. It does this while constructing the background from video memory. OAM is inside the PPU, so it can read the background at the same time. It reads Y coordinates to find the frontmost 8 on each line, then it discards the rest. Games have to alternate the order of sprites in OAM so that characters don't become invisible when there are more than 8. This is where flicker comes from. At the end of each line, the PPU knows what sprites are in range. It fetches their patterns from video memory between background lines. It shares address generation timing with background patterns. During the first 64 pixels of a line, the PPU clears a buffer called secondary OAM. This is the scratch pad listing sprites in range. After this, it reads each sprite's vertical or Y coordinate. A sprite is in range if the current scan line minus its Y coordinate is between 0 and the sprite's height, which is either 8 or 16 pixels. If in range, it reads the tile number, flipping and color attributes, and the horizontal or X coordinate. If out of range, it skips ahead instead. Time to refresh my memory on what sprite evaluation does once it has finished reading the list for this line. The PPU displays 8 sprites on each scan line. One of its status flags is supposed to indicate when it missed some, but a minor bug in the PPU causes status to be inaccurate. When looking for a 9th sprite, it reads OAM diagonally and actually treats values other than Y coordinates as Y coordinates. This causes both false positives and false negatives unless the 9th sprite directly follows the 8th in the OAM. I added definitions for the 3 status flags. Descriptive names make it easier to reason about the code than having literal numbers all over the place. I made my first draft of sprite evaluation compile. Day 3 of Sprites. Yesterday I added a way to dump OAM. Today I added it to the help text. As with the background, I used logging to debug sprite evaluation. The Game Boy scene calls this process OAM scan. I used a good emulator to find which scan line to log. My log didn't look right near the end. It wasn't clearing the source address to 0 at the end of the line. I added a way to end the diagonal pattern. There are 2 variables for sprite 0, one if it's visible on the next line and one if visible on this line. With OAM scan looking closer to correct, I calculated which address the PPU reads to fetch sprite patterns. I added names for the flip, priority, and color attribute bits. Vertical flipping controls what pattern address gets fetched. I tweaked the 9th sprite diagonal fetch pattern. Like the background, the sprite unit holds 2 bit planes and unpacks bits into pixels using shift registers. There are 8 shifters, one for each possible sprite on a line. All the shifters run at the same time, and I needed to clear those shifters when the PPU powers up. I copied the sprite patterns from the read buffer to the shifters. Unlike background tiles, sprites can be flipped horizontally. This corresponds to reversing the bits in each byte. I looked up efficient ways to reverse bits on a web page about bit manipulation. Tomorrow I expect to clock the shifters. Day 4 of Sprites. I'm running out of time to get a game playable by Christmas. First, I refactored bit reversal to a function. I reminded myself what data I was looking for in fetches. It turned out I hadn't finished calculating the fetch address. I needed to find a sprite row with all 3 colors to make sure I was reading the right data. And I was. Time to write the shifters. For each pixel, it counts down all sprites' X coordinates. Once the sprite's X reaches 0, it reads 1 pixel from the pattern. The frontmost solid pixel among all 8 wins. Because I already had the background pixel, I could tell whether both the background and sprite 0 are solid. The frontmost sprite wins even if it's set to behind the background. A sprite can push the background forward in front of other sprites. Games relying on this include Dizzy, RHDE, and Full Quiet. Sprites are evaluated and fetched on one line and combined with the background on the following line. That's why I added one to the scan line for logging here. Did I do it? I think I did it. We have a sprite in the output. Now let's get sprite 0 going. I figured out where it should be to log that scan line. The moment of truth? And we have sprite 0. It turned out OptiPing, the tool that I use to recompress ping images, can also convert PPM to ping to post in a forum or chat room. That's convenient. Seeing that title screen intact is such a morale booster. It looks like I might get interactive tomorrow after all. I did something sneaky here. I stored data that the DMA unit reads in the CPU's open bus. It's sort of reminiscent of how DMA on the Super NES works. It sure as heck wouldn't work that way on the NES with a power pack with its pull-up resistors to stabilize the data bus at all ones. Once I had sprites kind of working, I switched the get and put cadence to the end of a CPU cycle. That needed some changes to the OAM DMA state machine. I got done everything I set out to do today with a few minutes left. I used that time to introduce the concept of buttons to the system. I'll need those when I go interactive tomorrow, hopefully.